Problem 6, suppose a function is continuous on the closed interval 0, 1. So you don't know what this function is, but you know this function is continuous. Okay, on the closed interval 0, 1. Okay, and you know the function, the value is always between 0 and 1 whenever x is between 0 and 1. Okay, this is very important. You don't know what this function looks like. You don't know its value, but you know the range of its value. For every x between 0 and 1, fx is also between 0 and 1. Okay, so how can we translate it? How can we put that on a graph? So on the graph, it's continuous from 0 to 1. Okay, we can draw this square. We can draw this box. Okay, you can see fx, we don't know its shape, but we know that fx must be residing in this box. Okay, fx could look like this, fx could look like this, fx could be a straight line, fx could be like any curve, right? But fx must be in this box. Why? Because whenever x is between 0 and 1, your fx value is also between 0 and 1. So you have this 0, 1, 0, 1 box. Okay. So, question, is it true that fc is equal to c for some c between 0 and 1? So is it true that fc is equal to c for some c between 0 and 1? Okay, let's use a mathematical symbol. Some c between 0 and 1. Okay. So clearly we are going to use IVT, right? So how do we construct such a function? So fc is equal to c, right? A solution of fc is equal to c. It is also a solution of fc minus c is equal to 0, right? A solution of fc is equal to c. It's also a solution for fx minus x is equal to 0. Okay? So we can call this fx minus x our function gx. Okay? So now we are trying to find out whether this gx is equal to 0 has a solution between 0 and 1. Okay? Whether this gx is equal to 0 has a solution between 0 and 1. So we'll talk about g0. We'll talk about g1. Right? What is g0? g0 is f0 minus 0. g1 is f1 minus 1. Just do the substitution, right? g0 is f0 minus 0. g1 is f1 minus 1. Okay. And we want this to be, okay, then it's just f0. Okay, do we know anything about f0? Yes, we do. Because your fx is always between 0 and 1. Okay, so we know this f0, it will be greater or equal to 0. Okay, we know this f0 will be greater or equal to 0. Okay, so there are two cases. What if f0 is equal to 0? Right, if f0 is equal to 0, then you already solved the problem. The problem asks you, is there a c such that fc is equal to c? Right, if your f0 is already equal to 0, then your f0 is equal to 0. So the c is just 0. Right, so it's already a solution. So that would be the first case. Okay, first case, f0 is equal to 0, then your c will just be 0. The statement is true. Okay, so this will be our case 3. Okay, so if it's not the case 1, right? If it's not case 1, if f0 is not equal to 0, then f0 must be strictly greater than 0. Okay. So here we divide it into 3 subcases. Okay, first case is just f0 is 0. Then the second case is just f1 is 1. Right? Then already when c is 1, the statement is true. Okay. Otherwise, when f1 is not 1, you can see originally here f1 is smaller or equal to 1. Right? Why? Because again, fx is between 0 and 1. Okay, fx is between 0 and 1. But if f1 is equal to 1 is excluded, then your f1 is just smaller than 1. Okay, so minus 1, it will be just smaller than 0. Okay. So now, if G0 is greater than 0, G1 is smaller than 0, then by the intermediate value theorem, there's a C, there's a C between, there's a C on the interval 0, 1, right? Such that GC is equal to 0. Okay, GC is equal to 0, which means FC minus C is equal to 0. Okay, which means, FC is equal to C. Okay, so in all these 3 subcases, the statement is always true. So overall, the statement is true. Okay.